recording. Okay, sorry you missed the beginning of my introduction, but you won't miss my introduction to Jeremy. Jeremy is MIT Lincoln Lab Fellow. He founded the Lincoln Lab Supercomputing Center and still heads it. And he pioneered the establishment of the Massachusetts Green High Performance Computing Center. He has developed novel big data and parallel computing software used by thousands of scientists and engineers worldwide. He has led several embedded computing efforts. It earned him a 2011 R&D 100 Award. He has chaired the SIAM Data Mining Conference and the IEEE High Performance Extreme Computing Conference, as well as the IEEE Big Data Conference. He is the author of 2 best-selling books, Parallel MATLAB for Multi-Core and Multi-Node Computings, and Graphic Algorithms in the Language of Linear Algebra. His peer-reviewed publications, including works on abstract algebra, astronomy, astrophysics, cloud computing, cybersecurity, data mining, databases, graph algorithms, health sciences, plasma physics, signal processing, and 3D visualization. In 2014, he received Lincoln Laboratories Technical Excellence Award. And with that, I'm going to turn it over to him, and he's going to tell you how Lincoln Lab handles distributed arrays in a way that makes AI computations scalable. And with that, Jeremy will take over.
Well, Peter, thank you so much for the introduction, and it is a real pleasure to be here. We have a very large online audience, and we're, so this audience is really going to be speaking probably mostly to that bigger audience, but we have a great audience here in the room as well here at MIT CSAIL. So with that, the title of my talk is Easy Acceleration with Distributed Arrays on the world's largest interactive AI supercomputer. I, of course, want to credit our whole team that builds the supercomputer and makes all these things possible. And really, I'm representing their work today, and they're listed here on the title slide. So this is a brief outline of my talk. I'm going to first give a little overview of what really interactive supercomputing is. It's something that we've really been focusing on at our supercomputing center for a couple of decades. Then I'm going to talk about how AI and supercomputing fit in there, and then get into this core technology, which we call scalable distributed arrays, which has been kind of a backbone for a lot of our scalability and has kind of very nicely layering into the new capabilities. And I'll talk about some of the performance results we have there. So just what is the Lincoln Laboratory Supercomputing Center? What is our role? Well, Lincoln has a number of mission areas. In general, Lincoln's main thing is systems analysis and architectures for domain protection. So if there's a domain that needs to be protected, land, sea, undersea, airspace, cyberspace, Lincoln's main job is to kind of figure out how to do that. What is the architectures for doing that? And what are the technologies needed? So this work generates an enormous amount of data because protecting domains usually involves sensing those domains and a corresponding large amount of computation to just figure this out. And so our supercomputing center develops a unique energy-efficient supercomputing. The key to our success is really vertical integration. So if you want to get more performance, vertical integration is a great way to do it. So we vertically integrate around our core mission, which is doing science and engineering, analyzing large data sets from the data centers and the type of power that they get all the way up to the computers, to the software stacks, to the way the users work with them. And so we do pioneering research in these areas from data centers, hardware, software, and user support. And so as a result, for the kinds of things we do, and remember, we're pretty narrow. We're not doing YouTube. We're not doing LinkedIn. We're not doing a whole bunch of other things that other people have to do. We're about 100x more productive than standard supercomputing and 100x more performant than you would get in a standard cloud. And I'll also say we kind of have an unfair advantage in that our team is pretty much entirely MIT people, and our user base is almost entirely MIT people. And I'm sure if you went to any large provider and said, like, You just have to focus on that. They probably could do a lot more than they're doing as well. So we do have the tremendous benefit of working with this really brilliant user base. And so we can do very sophisticated things with them. So the core interactive productivity challenge in computing and supercomputing and AI computing kind of looks like this. So we have this plot here, and the x-axis sort of represents time, and the y-axis represents the useful work done. And in almost any system in the world, someone grabs, reserves capability, and then they start a workflow that sort of looks like this. There's a period of time where they're setting up and launching whatever they want to do. They usually are engaging in some basic, IO or other types of stuff. And then they get to the point where they really are using the system to maximum extent. And then that stops, and they kind of oscillate in this cycle for a while. And then they have a tear down and kill time, right? So this is really kind of what you typically see in many places in the world. And the key thing to understand is that the core productivity metric we're sort of interested in general is performance per cost, right? You can always increase performance by just buying more stuff. So you have to normalize it by cost. And so that productivity is, simply the amount of work you're doing divided by time, divided by cost. And since increasingly cost and time are interchangeable, right? The amount of time it takes, the amount I pay to rent some capability or have some capability is generally proportional to time. It means that this time thing is really very important. It goes as the square. So if I can reduce the time it takes for someone to get their work done by a factor of 10, I've actually, increased my productivity by a factor of 100. So how do we go about doing that? So we kind of invented these metrics 20 or some years ago, and we've been architecting our supercomputing centers around them for a couple of decades, and have built a lot of technologies to really go after this core question. Because what we really want to do is do this. We want someone to just start immediately, don't worry about setup and launch. They're using it full speed, and then someone else can use it, right? That's essentially our overall goal here. And so how do we do that? So there's a number of things, and I'll talk about them today. So in particular, first off, we have a lot of things, and I'll just mention them in the setup and launch, tear down and kill, and how do we measure efficiency? How do we expose to the users how they can know if are they using the system efficiently? And so we have a number of things. I'll briefly discuss those. And then I'm mostly going to then talk about how do we help users really get scaling and optimization and get performance, right? So you need all of these things to kind of really do this well. And so I'm going to kind of talk a little bit about the first three, and then most of the talk is going to be about the last bullet there. So the key thing with setup, launch is just starting fast, right? We want to do interactive things. We always tell people that our supercomputer is just like a laptop, but when they connect to our system, it's just a bigger laptop, right? They can now work on terabytes of data, on thousands of cores. They hit return and things happen immediately on thousands of cores. That's the experience that we try and maintain. And so as a result, we've probably put more time and energy into figuring out how to get things started really, really fast, whether it be thousands of Windows instances or MATLAB analysis environments or AI processes. We can start these things faster on thousands of computers than you can start on a laptop, like by itself. So we've really pushed the limits in that. There's a bunch of things we do behind the scenes to make that happen. But this way, for the users, it's the same experience they have in the environment they like on their laptop, but it's just starts immediately, and they're doing much bigger problems, which is essentially what we're trying to do. So one of the ways we do that is we have some very innovative, what we call allocation technologies. When you have a supercomputer, the way it's traditionally treated is that you have a bunch of cores, which are just slots that can be filled. And if someone says, give me 10,000 cores, which equals 10,000 jobs, it will just sort of stripe those jobs across the system. And there's really no ability to optimize for the memory core hierarchy that is inherent in all of these computers, which is really key to getting good performance. So one of the things that we have that's special about our system is this special hierarchical allocation system, where we expose to the user the three core sort of things they're going after when they get a computer. How many physical compute nodes do they want? Do they want 5, 10, 100 compute nodes? How many processes do they want to be running? So how many instances of their program they want running on each one of those nodes? And then for each process, how many threads do you want to devote to computation? And the product of those is essentially the number of cores that you would be really using, or a number of computational slots. So that's how the users launch their jobs, is what we call these three parameters, which we sometimes call triples mode. Our allocator system divides the work up amongst the nodes, and the scheduler just deals with the nodes. Like the master scheduler, all it does is launch. If you say, I want to run on 10 nodes, it says, I'm running 10 jobs. And then what happens is that we dynamically write a little mini controller that runs locally on the node that sort of manages all the processes and threads for that. And so it's completely distributed. So one of the key ways to get launch time down is to distribute the work of launch, right? Most of the times the real bottleneck is the centralized scheduler, but we just say, well, you just have to do 100 things. They can do that very fast. And then the 10,000 things is happening distributed locally on all the nodes. So let's walk through what that looks like. So in this case, a user requests one node with 16 processes, 4 threads per process on a computer that has 64 cores, right? So the mini controller then says, aha, I'm going to look at this computer. I'm aware of the geometry of the chip. I recognize that certain cores are closer to each other in the memory hierarchy than others. So I'm going to divide up the chip into 64 pieces that have that knowledge. And then I'm going to launch each process into one of those pieces. And I'm going to bind the process to those particular cores. And likewise, the child threads will also be bound to those cores. And so this allows us to launch this very quickly, and also get the added benefit of properly sort of laying the process and the work down on the chip so that it can get maximum performance. So in addition to this giving us fast start, right, you know, it also helps with fast kill or fast ending, right? So here's an example of how you know, hierarchical allocation performance happens here. So we're, you know, launching a few thousand, you know, nodes on processes onto 512 nodes. And you can see with our system, the hierarchical system, it just starts immediately, does work, and then stops, right? Exactly the way you want it, like the way you would like it to be in an interactive system. But if you, and this, we have a highly, like the scheduler we use is especially tuned to do this stuff very fast. But even the way we've set it up, the blue line shows if you just submitted those 4,000 jobs to the system, what would happen? It would take, you know, 60 seconds or so before everything got started. And then once things were done, there'd be a long tail of, you know, another few minutes. Now, in most supercomputers, this is okay. In fact, in a lot of cloud systems, this is okay because people will start, but they're really going to be using it for, you know, hours on end, but it's also going to be mostly idle during that time. So they're reserving it. They're going to reserve it for a long time. But if we recall that workflow, there's going to be a lot of like, well, they didn't really need all that expensive gear all the time. So this system allows us to dramatically make it so stuff starts really quickly, gets full performance, and then gets out of the way, you know, really, really quickly. So another thing we do is innovative scheduling, right? So, you know, there's kind of two basic ways to run a supercomputer. There's sort of what's called the batch mode, right, versus interactive. And this is just queuing theory. And you can see it if you go to any retail store. You can tell what they value. If they value the time of the customers, you'll see a lot of checkout lanes, maybe a lot of people servicing those lanes. But at any given time, a bunch of them are going to be idle, right? So that's cost, right? That those folks are idle, but you as a customer, you get to race through the system pretty quickly. Likewise, if they want to save price, they'll have one checkout lane and there's 50 customers waiting behind it. And then that checkout counter is fully utilized. Exact same thing happens in supercomputers. Many supercomputing centers, a figure of merit is, the overall utilization of the system. They want to achieve 90% utilization. Sometimes a figure of merit is how long you have to wait. Like if they have a 9-day queue, that's considered a great thing. It's like a really fancy restaurant where like, oh, you have to wait, weeks before you're going to get a reservation. It must be a really great restaurant. So likewise, if you want to do interactive, which is what we want to do, typically you're going to hit 50% utilization because you always have to have stuff available for people to run on. So I'd say in both cases, the wall clock performance for the user is the same, because generally in batch systems, there's a thing called time dilation, which is 2-to-1, which is so for every hour you're running on the system, you had to wait an hour. So if you're going to do 10 hours of computation, you probably needed to wait 10 hours for the job to start, versus an interactive system where you could have as many nodes, but it would run immediately, but it would take twice as long. Again, this is just queuing theory. There's nothing we can do about it. It has nothing to do with computing. So, but what can we do to get the best of both worlds? So we do something which is called spot jobs, right? And you sort of hear that in the cloud world, but we can figure out how to layer this so that we have both our interactive things. So to the users that are using interactively, it looks like the system is 50% empty, but they don't see is that there's all these spot jobs running in the background, filling in those gaps that can be preempted very quickly, so quickly that there's no delay or impact on the user rule. And so this, the hierarchical allocation that I talked about before really also enables what we call fast kill. And so as an example here, so if we want to preempt, a 4096 processor job using our standard approach, it would take about 80 seconds. Now, most places in the world will be like, wow, that's really, really fast. But if I'm hitting return and I want an interactive experience and I'm now waiting 80 seconds to launch my job, then the user doesn't like that. But with this fast kill ability, we can kill those jobs in less than a second. And so the user doesn't even know that they've launched a job. It needed to go and kick out some spot jobs in order to do the job. And this allows us to have the best of both worlds, where we can have both interactive computing and spot jobs going on in the background to fully utilize the system. So this is another capability that we pioneered to do this kind of work. Once you get the fast start and the fast launch, you have to show users. The great thing about interactives is they're launching right away and they can see, is the computer being used fully, right? And so we have tools that we have built that a user can just quickly type a command and see, oh, how many cores am I using? What's the load am I inducing on the system, right? So if I have like a 48 core system, I'm kind of looking for a load in the 20s, 30s, maybe 40s, and then I'm probably, using the system. Load is a necessary but not sufficient condition for performance. You cannot get acceleration if you aren't actually using the computer, right? So you have to be inducing load. Now, that doesn't mean you can't induce load and still be running slowly, but you have to be inducing load in order for it to be running quickly. Likewise, in our GPU nodes, someone can be running and they could be having a lot of CPU load, but we're not seeing any GPU load. This is actually surprisingly common. And in fact, most folks would take a lot of education to use, say, a large GPU system and have those load numbers come in high all the time. It's actually quite tricky to do. And so this is another thing the users launch right away. They can type this command and you're like, oh my goodness, I'm not using the cores. Why aren't you using the cores? Maybe I need to use a different triple configuration. Or why am I not using the GPU? I need to figure that out. And they can also then engage with us and we can help them figure out these things. Because for us, because it's a finite system, the best thing we can do is get them to get their jobs done quicker, right? They're not there to just consume computing. They want to get their work done fast. We want them to get the work done fast. So we can work with them very closely on this. In addition, to help us, we can have weekly efficiency analysis reports where we collect all this data up for the week and we can identify for us users with low GPU load, low core load, high core load. That can be bad too if you go too far in the other regime. And then we can reach out to these top users and say, hey, we're noticing this. Let's work with you to get this more efficient because it will help your jobs run faster, and then the system is bigger for everybody. And so for us, why we're so interested in efficiency is that that's the easiest way for us to make the system just bigger. If we can get everyone's jobs to run 10 times more efficiently, our supercomputer just got 10 times bigger for no money. And so we love that. Now, we have other things here. So let's feel like we're at MIT, right? So of course, we have things beyond just the traditional text views. We were amongst the pioneers to use advanced gaming technology to create full 3D digital twins of our supercomputing capability. So we did this starting in 2010. So this is not just a mock-up. This is real. Like, these are screenshots from a system that's a full 3D representation of our supercomputers that are getting live telemetry from the computers. You can click on the nodes, see who's running on them, see what the loads are, see the various alert. We also have completely tied into the entire electrical system, so we can see the fans, the cooling, the whole system, and get a full interactive view of the entire system. And this allows us to kind of manage the system holistically. And it's also very good for things like physical inventory, which actually you can imagine when you manage thousands of computing nodes, like knowing where things are and where things are physically is actually quite important. This can further extend down into the node itself. So we have sort of cartoonish representations of what's going on actually in the node itself. So here's a typical GPU node, and we have it's like represented as a factory where we have, data storage, memory, solid state storage, vector units, CPUs, and GPUs. And when this is running, these things all light up with how much they're filled. In fact, we even have an ability to do kind of playback, where if someone was running a job on a node and they wanted to see, well, how did this go over 24 hours? This thing could animate and show you what was happening over a 24-hour period. And this is a great way to teach folks about, what's really going on, how are they really using the computer. At a minimum, at any given time, we want them to see maxing out some part of the system, whether it's the memory or the GPUs or the vector units or the cores. It should be limited in some way by the physical limits of the system, and that's an indication that they're actually using the system efficiently. All right, so that's just kind of some of our kind of great work we've been doing to make those first three pieces of interactive supercomputing go well. Let's talk about, the current drivers, which are, AI. So, pat ourselves on the back. We just deployed our new system, which is called TX-Gain. It's the largest AI supercomputer at any university. I would argue it's the largest interactive AI supercomputer in the world. Well, one, there aren't that many supercomputers in the world that are interactive. In addition, if I'm 100 times better than anybody else, that makes my system that's much bigger. This is a significant increase in our computing power. The backbone of this are the 600 NVIDIA H100 chips, as well as the AMD EPYC chips. And this was a Hewlett-Packard enterprise system. And, some of the, metrics to really kind of look at here are the total peak petaflops. This is double precision matrix petaflops here, 42 petaflops. But there's this thing called AI flops, which are much lower precision, and that's really a huge number. And so when we program this system, these are the things we're really looking at. Are we allowing our users, who are scientists and engineers, who really don't want to spend too much time figuring out how to optimize, get, significant performance out of this system? So a big driver, of course, is AI. And, if you look at history here, if you look at the number of parameters that you see in these AI models, it's grown dramatically. Remember, this is logarithmic in powers of 100, right? So there's just, about 12 orders of magnitude of growth in the size of the parameters. The first dot here is from the first neural network model that we did at Lincoln Laboratory in the 1950s, probably one of the first, certainly the first digital computer to ever do those models. And then we had this sort of pre-deep learning era where kind of these models were doubling every 1.5 years. Then we get into kind of the deep learning era where the models are doubling in size sort of every half year. And then now this sort of new transformer era, the large language model era, where the models are doubling, every every few months, basically, in size. And naturally, the computational requirements of these models are going up in proportion to their size. So this is obviously a huge driver of computation. So of course we support, large language models are all the rave, and we support the same interactive model for our large language models. So people can come to our systems. We support many, many models. That's just a demand signature. People say, hey, can you support this model or that model? And then we have an interactive system where they can start the models, using something called VLLM, and just through Jupyter notebooks or web interfaces, their own copy of the model is spun up on one of our compute nodes. It's completely isolated. They don't have to worry about it accidentally reaching out. They don't have to worry about, their queries going into some place that they have no idea what's being done with their data. And so this allows us to do a lot of research in sort of figuring out what these models are good for. And there's a lot of our sponsors that are really come to us to say, can you help us figure out what models are good for? And obviously we need separate systems to be able to do that, because we'll be dealing with the data that our sponsors provide us, and we don't want that data just going anywhere. We want it to be in a highly contained environment where we can do very detailed experiments to figure out what works on these systems. So let me just kind of review for those who aren't familiar what this whole AI landscape looks like. So, in gray here, we have all of AI. And then a subset of AI are large AI models. And arbitrarily, we'll say those are models with, say, 1 billion parameters, right? You can just think of big giant matrices or spreadsheets that have 1 billion cells in them, right? That's really all it is. And then a subset of those large AI models are language models. GPT, Llama, DeepSeek, there's thousands of these now, these models that sort of really deal with human language and natural language. And then some of those have been made into commercial services, like Microsoft ChatGPT, Google Gemini, Anthropic. They all have commercial services, which people are using for Office and email and calendar and all the things that you see people using it for. So in the research area, we're really focused on these kind of two areas here. We're not really dealing with commercial services. We're dealing with domain-specific adaptation of large AI models, including language models, to specific data sets to incorporate specific goals. So people are trying to figure out how to make these models more specialized, because there's big opportunities there, right? If I want to create a model that's really good at, say, acoustic processing, does it also need to have the entire who was the batting champion in 1877, right? I mean, it's all in there. And the key that people are trying to figure is, how do I get rid of all of that stuff and have a model that just does what I want, which, one, will be a lot more efficient to run and won't hallucinate about things it shouldn't know about. If I'm just asking for acoustic signatures, it shouldn't accidentally tell me about, and the King of France was this, right? So these are the things we're trying to get done there. So there's an enormous amount of work to figure this out. It's a tremendously exciting time. And then I would also say, particularly for, our research lab, there's a lot more modalities of data besides language. Yes, we're using language in things like OSINT and malware, but really all these other modalities are generating far more data. And so a lot of our work is figuring out how to make AI good for every other modality on Earth, right? Yes, we're definitely helping people with large language models, but there's all these other modalities, and we're focused on that as well. And that's why we need our own systems to be able to do this work. A great example is something called Gen AI for Science, right? And there's this great paper that was published. It's really more of a book that just talks about how AI can really help, fundamental science questions, whether it be, quantum mechanics or molecular interactions or modeling proteins. This has become a whole new sort of field. And, we're really proud that about 60 of the 60 authors, 14 are from MIT, and that our supercomputing center, 13 of them were users of our supercomputing center. And that was a conscious decision we made many years ago. We really want to support AI for doing scientific exploration and advancing fundamental science. And we're really pleased that this field is really moving forward dramatically. So what's this all about? So I've laid the groundwork. What are these computers really, really, really doing, right? Well, it turns out they're only doing one thing, which is called matrix multiplication. And in fact, I was on a panel, a few months ago, and I'm now old enough that I'm the graybeard, right? And they turn to me and they say, Jeremy, you've been doing supercomputing for so long. Isn't it amazing to see how much things have changed? And I'm like, they haven't changed at all. The only thing we've ever been able to accelerate is matrix multiplication. Our supercomputers have only done that for like 50 years, right? It's just a lot more people can use it. It's the only thing we know how to build. And in fact, if AI could not take advantage of matrix multiplication, we're not talking about it. We're talking about something else, because matrix multiplication is the only thing that we really know how to build fast. And so this is an example of the specs from the chips that we have, and they're truly mind-boggling. 60 teraflops of double precision performance. And then up here, you're seeing like 3 petaflops of lower precision performance, right? And so double precision matrix multiply, which in the business is often just called DGEM, and I'll have more on that later. AI has been the core for decades, but AI has added a whole bunch of new things, like all these really interesting smaller precisions. And soon we may have truly arbitrary small precisions with some fascinating sort of number theory derived stuff, often called the Ozaki scheme and variants of that. So we might be able to do all the precisions with sort of one type of computing. AI is adding new formats, sparse formats. That's where the matrix has lots of zeros in it. And in fact, this little star here means, oh, by the way, in order to get this performance, your matrix should be about 50% zeros, which is actually surprisingly common, right? So they've been looking at sparsity. We could be talking about hypersparsity, which is super sparse matrices, and we're adding new operations. This matrix multiply is usually doing traditional arithmetic addition and multiplication, but for a key part in deep neural networks, something called the rectified linear unit, which is the most complicated name for about the simplest function you could have, which just says, if the value is less than 0, make it 0, and if it's not, leave it, right? So that's what the rectified linear unit is, but that adds new types of operations, something called max plus algebras, which is a form of mathematics sometimes referred to as semi-rings, which basically allows us to pair many more types of operations. So let me explore this a little bit more and explain fundamentally why this is the operation we know how to accelerate. So I've blacked the screen because we're going to do sort of chalkboard time. So hopefully I'm not giving anybody sort of bad flashbacks to math class. So we're going to go deep and we're going to bring you back to elementary school mathematics here. So here's an equation, right? 2 times 3 plus 4 is equal to 2 times 3 plus 2 times 4. And so hopefully my MIT audience here can tell me which mathematical property this is illustrated. Close. Distributive property. And in fact, this property is really, you could argue, kind of why math works. Like, if this isn't true, when someone thinks about math a few 100,000 years ago, like, it kind of doesn't go anywhere, right? Like, this is not a useful thing. Without the distributive property, like, math is pretty darn useless, right? And now I'm going to do advanced math. And you always know we're doing advanced math because we start putting circles around multiplication and addition. And that's kind of the warning sign. We're going to do advanced math now. Okay, so don't be afraid. I've just put circles around multiplication and addition and basically just said, hey, by the way, one pair of operations that abrades this property is traditional arithmetic addition and arithmetic multiplication, the things you use every day, all the time. But there are other pairs of operations that obey this property. Max and plus. So that's kind of a mind bender, right? I swap, the plus operation for max, and then I turn multiply into addition. I always get that kind of confused, but Nevertheless, this is a big part of what's happening in deep neural networks, is essentially working over this kind of pair of operations, which still obeys the distributed property. And then likewise, you could also use set things like union and intersection. This is the basis of something you may have heard of called SQL. So whenever you're doing relational databases or any kind of database that's over SQL, it's literally just the same type of operations, but it's just doing union and intersection. And the reason they can optimize your queries is because there's essentially the equivalent of a distributed property going on inside the database. So now let's take it up a level in abstraction. So I can now use letters instead of numbers, right? Hopefully I haven't scared anybody. And we have, before I just had scalars, right? 2, 3, and 4, were my numbers here. So that's all good. But I can do other things like A, B, and C can be matrices, and this property still holds. A, B, and C could be graphs or networks. This property still holds. They could be database tables. They could be spreadsheets, right? I'm giving you the math of Excel, right? Like this is actually, you can represent spreadsheets with algebraic expressions. And today, large language models as well. So, but what I'm going to explain to you is that all of these are a special case of kind of a new mathematical object we've been working on called associative arrays, right? So whether any one of these, any one of those pairs of operations, they all fall under this bigger thing called associative arrays. So let's explore this a little bit further. What does the data structure look like that holds these objects? So here's our matrix maybe, or our spreadsheet. It has a row, and it has a column, and it has a value. And so each of these is drawn from a set. So the indices are drawn from a set. The row and column indices are drawn from a set. The values are drawn from a set. And when I do matrices, graphs, and networks, typically these sets are I and J for the integers, and perhaps the real numbers for V, right? And that would be the typical matrix, right? Well, for database tables, spreadsheets, and LLMs, we now have a new term, right? I, J, and V can be tokens, which sort of recognizes that these are more abstract. They can be numbers, they can be integers, they can be words, they can be strings, they can be a whole range of things, but we just call them tokens, right? And formally, associative arrays have given us a rigorous mathematical abstraction to tell us what those tokens really are. Because associative arrays in I, J, and V are what we call strict, totally ordered sets. It just means a collection of objects that you can order, and you can always compare and say, this goes before that, or this comes after that. And essentially, associative arrays allow us to capture that and to capture all of these things. And whether they be large language models or matrices, we have sort of an overarching mathematics for this. Fundamentally, though, the reason we can do these computation fast is because of that distributed property, right? When I multiply two matrices, I have many, many, many multiplies that can happen, many additions that can happen, and math says it doesn't matter what order they happen. And so therefore, they can occur concurrently, which means I can take advantage of parallel computing. Because the clock rates on these computers have not improved in 15 years. All that's happened is that more things can happen at the same time. And so matrix multiply, for these mathematical reasons and for some physics reasons, this is the reason why we can do this. All right, and if you want more, of course, I've told you about me, buy our book from MIT Press. If this kind of thing is interesting to you, it really goes into the stuff in great detail. So now let's get into some of the special methods we use for taking things like this. And, when people want to do math on these kind of objects, which is basically anything, and how do they get good acceleration on our supercomputers? And so our motivation here, and this was something that we really pioneered 20 years ago, is that high-level programming language like MATLAB, Python, Julia enable millions of programmers. It's the level that they want to work in. When we started doing this 20 years ago, this got you kicked out of the supercomputing club, Like, how dare you sully our supercomputers with terribly inefficient languages like MATLAB, Python, and other things like that at the time, right? And we're like, no, 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 this is what people want to use. This is how they want to get work done. And now today, we want to use these on GPUs. The CPUs continue to get faster. Let's not forget, it's not like GPUs are just racing ahead and CPUs are doing nothing. They're continuing to get faster, and the cloud systems are growing to millions of computers. How can we make it easy for people who just want to do math, which is what we want to do here at MIT, to take advantage of these capabilities? So the challenge is, how do we maintain that ease of use while getting high performance and scaling both vertically, so that's within a compute node, horizontally, across compute nodes, and temporally, how do we make it so we don't have to redo this every single time we get a new computer? If someone gets this right and we upgrade computers, then they can still get good performance and don't have to go back to square one and figure this out again. So there's a number of parallel programming models out here, many of which have been pioneered at MIT. There's thread-based models for dealing with threads that can see the same memory. These are very powerful tools for doing low-level computations. In fact, most of the high-level computations that I talk about ultimately call a library that's been written by others that uses one of these techniques, whether it's on the GPU or the CPU. You're going to be using this model at some level. Likewise, if we want to scale across compute nodes, message passing is a very common thing. There's a standard called MPI, which is sort of a foundation for if I want to get multiple computing nodes working together, how do I do it? There's also classic, what we call client-server map-reduce models. This is a very common case where I have a whole bunch of work. I want to send it out to a bunch of compute nodes, and there's going to be one compute node that's just going to coordinate, right? It's just going to deal out work to others. The compute nodes don't really need to know about each other. They can just do the work. And then finally, there's this rarer model for people with who were not afraid by that math that I gave, called distributed arrays, which stands for partition global address spaces. And this has kind of been recognized as the kind of best combination of productivity and performance since the 80s, right? This model was pioneered right here on the connection machine. There was something called Connection Machine Fortran, which did these models. And if you are kind of really comfortable with thinking about things in 2 and 3Ds, this kind of model gives you extraordinary scalability and great performance. So it's not for everyone, but for the kind of people we have here at MIT, it's a great model. So what's the basic idea here? So let me first just kind of shout out to the different languages we've been interested in. We've been doing this with MATLAB for well over 2 decades. This is kind of our original killer app. MathWorks has then popularized this, and you could argue there's been more parallel programs written in MATLAB probably than any other language at this point. Likewise, we were one of the original sort of founders of the Julia language, which has become very popular. And Julia, everyone in the world, whether you use Julia or not, has benefited from Julia. Because until Julia came along, it was just accepted that high-level language were going to be an order of magnitude two slower than a low-level language. That was just accepted. And Julia said, no, 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 we can do very advanced compiler things. We can use this thing called LLVM to work on any different kind of hardware. And they kind of showed that you can make high-level languages run very close to the speed of low-level language. And essentially the reason that Python is much, much faster today than it was is because Julia paved the way. And all the other high-level languages now, leverage that. And likewise, because Python is so popular, we are, of course, applying these techniques to our Python user base. So I'll skip over this in the sake of time, but here's the key concept. I have some matrix or image or some kind of thing here, and I want to divide it up so that different nodes, processes, threads, GPUs can work on it, right? And the key thing is this concept of a map, right? Where I say, okay, I have my thing, and I'm going to have 4 things I want to divide it up on here, and this is I'm going to divide it up amongst the columns. It's a 1x4 map. Likewise, I can do the same thing for the rows. I can do it in 2 dimensions. I can do it in dimensions and have overlaps so that if they need to share some data for neighbor calculations, this can be done. And the powerful thing about this is it very naturally fits into the way we think about programs in high-level languages, where we often begin with some big high-level object like an array or a list of files or just some kind of big thing. And what the big idea is, we're discovering the concurrency from locality. Let me pull that apart for you. When people begin doing a programming and they try and do parallel programming, they're often it's a mystery to them. Like, well, how do I find things that can be done at the same time? You look at your program and it takes a while to learn that. But once you learn that, you see that parallelism is everywhere in programs. It's all over the place, particularly if you're dealing things with like matrices, because they have so much things that can be done in parallel. And so once you realize that, oh, I don't want to just make my program parallel with the first thing I see. There are better ways to do it. And the key is to do it in ways in which the data for the computation will stay local to the computation. It doesn't need to get broadcast all over the place. And so when you begin by taking the most important data structures in your program and chopping them up, you naturally get this. So you naturally get kind of the best type of parallelism. And so that's what we have been able to do, is we just teach people like, hey, find your biggest data structures, add these maps to them, divide them up, and then guess what? You probably have a pretty good parallel program, right? Just there. Not always, but most of the time, it's the best way to start. So we do a lot of benchmarking, as you can imagine. My team is involved in most of the major supercomputing benchmarks in the world, right? Part of that is we do benchmarking to make sure that our systems run properly so the users don't have to figure this out. In addition, as a federal lab, kind of our job is to actually measure things for real and publish them so the rest of the world doesn't have to just like look at blog posts or marketing literature. We actually go and measure things rigorously and publish them so that people know what's really going on. And if ever you're going to do some kind of new way of programming, one of the most common benchmarks is a thing called the stream benchmark, right? It's been around for a very long time, and it just tests the memory bandwidth of your computer. And we've found for high-level languages, it's actually a really good benchmark, because high-level languages do tend to have a lot of memory movement, right? They tend to be more memory limited than compute limited a lot of the times. And so this is a very simple benchmark. It has 3 vectors, A, B, and C, and you begin by copying one to the other, and then scaling that into another, and then adding them, and then adding and scaling them at the very end. And often we just focus on this thing called triad at the end. Like when people give you one number for the stream benchmark, they'll often just say, this is your triad benchmark. And it's just a simple program that you can write that will really test the memory bandwidth that the compiler will not optimize away, right? So writing simple benchmarks is very hard because the compilers are so smart now. They'll be like, well, this is so simple. I know the answer. I can jump to the head, right? And in fact, probably if we have large language model compilers in the future, it will be very difficult to trick that compiler into like, no, I actually just want to measure the hardware, right? It's like, no, but the answer, I know it, you know? In fact, that was there were compilers that sometimes in the past that would recognize certain benchmarks and then just immediately jump to the answer and give you this, incredible performance. And so this is a real thing when you're doing benchmarking. So when we do this in parallel, this is what it looks like mathematically. I have my vector here. It's a row vector. I'm denoting that the dimension P is the one I'm going to be parallelizing on. So I have my 3 vectors. I'm breaking them up amongst different processors here, NB processors. And you can see that this computation can be done with absolutely no communication, right? That's what we want. This is called pleasingly parallel computations. This is you look for these are the winning ways to get really good performances. People are like, oh, but I want to do an FFT and I want to make that super fast. It's like, well, how many of those FFTs are you doing? I'm doing 1 billion of them. So if I just put 1 million of those FFTs on separate computers, that'll also work. And we'll go, yeah, well, why don't we do that? And we don't have to worry about figuring out how to make a very complicated operation fast. So just dividing up work and giving it to lots of different things that do computation is good. So this is how we write this program in parallel. This is the actual whole program. This is its pseudocode, right? This is what you do. You iterate, you declare your vectors, you iterate and do this over and over again so that you can get enough time. And then you just do each step with a timer around it, right? This is the serial code, and the parallel code is essentially identical, right? So we say we're going to chop up in this dimension, and then to force the locality, just so that people know that this is just involving entirely local things. We often have this .loc thing, which just stands for local. It means just take the local part of this variable and copying it to the other local part of the variable. No accidental communication can happen if I do this. I'm sort of guaranteeing that, nothing bad can happen from a communication perspective when I do that. So let me go implement this in MATLAB and Python using our parallel methods, right? So we have a little map here for chopping these up. All we do is allocate these arrays. In fact, we allocate them and grab the local part immediately, and then we're off to the races, right? And we just do our thing here. This is just the first one, and this is the Python code. Looks, very much the same. And so this is a really simple way to do this, and you can do it obviously for much more complicated programs. But the thing I want to highlight here is something that we just started looking at recently. It's like, well, I think the GPUs are a thing. Can we just do this with GPUs? And both in Python and MATLAB, you can just tag an array and say, this lives on the GPU now. And that's all you need to do. And the rest just takes care of itself, right? Just through implicit, essentially type promotion, it just takes care of itself. It's very impressive, right? So we can now look and see, how does this program scale? So let me go over the results. So first I need hardware, right? So I have, one of the great things about our system, we have lots of hardware. We can make it last a really long time. It all gets updated with the latest version of the software. And we've been doing the stream benchmark for a long time. So I'm going to show you data kind of goes back to 2005, because we've been doing this same benchmark for a very long time. And so we can see, how this all scales. So let's start with our GPUs, our brand new GPUs, right? And it looks great, right? This is linear vertical and horizontal scaling. So this is the single node performance, scaling linearly, and just keeps on going when we add nodes, where we have basically, this is the entire supercomputer, right? And both MATLAB and Python, we have hundreds of GPUs, it's in multiple languages, and we're achieving the hardware limits. This is great. Now we can give this system to our users and say, all right, we know that this system can perform well in the way you want to do it. We can look at the AMD chips as well. And, we get linear horizontal scaling, and we get pretty good scaling on the node itself. But as a memory bandwidth benchmark, CPUs, high core count CPUs tend to run out of memory, bandwidth when you do this computation. This is entirely expected, but you still get pretty good performance, being able to scale up there. And so this is great too. And we're getting essentially hardware equivalent performance, right? And we can do this. This goes back in time, older nodes, 2004. This is the 2004 data. I didn't have these old like we just took the data from the paper. So we've been seeing the same shape, same program, same scaling methodology has been working for generations. And this allows our folk to write the program once and have it know that it will they don't have to change it. We can add in new hardware and their programs will still work well. So, that's the 2005 system, I'm sorry. So, and so we can look at this cumulatively over 20 years and sort of map these trends, right? So these are the real kind of measurements of what's actually going on here. So we've seen about a 10x increase in single core performance over 20 years. We've seen about 100x performance increase in 20 years on the CPU node, right? And then the GPU has experienced about 5x performance in just the past 5 years, right? And this is all consistent with the hardware measurements. And most people are kind of really excited about this 15x jump that you get from going to the CPU node to the GPU node. And that's kind of why people use GPUs. So, exactly what we would like to see. Now let's switch to something else. Let's switch back to matrix multiply, right? I've shown that the memory bandwidth works. That's kind of a prerequisite. If the memory bandwidth isn't working, like everything else is going to get screwed up. So we make sure that that works. Now let's go to this thing that these GPUs are really designed to do, which is double precision general matrix multiply. This is where the DGEM comes from, if you ever hear that. Double precision general matrix multiply. So on our dual GPUs, we're getting 100 teraflops, right? The peak is 120. So we're getting like 80% from MATLAB or Python, right? I won't show it here, but we've run this across the entire system. I'm getting 30 plus petaflops just typing A times B in MATLAB across the whole system using this, right? That's amazing, right? No fancy coding. Any of our users can do this. We've seen a 7x increase in the performance of GPUs over this period of time. But the big thing is, because this is what GPUs do really well, is these matrix multiplies, there's this 1700x difference between the GPU and the single core on the CPU. And that's a lot of times what people are exposed to. In large part because a lot of times they don't have access to this distributed arrays. So they have no way to really accelerate on the node. So there's this 35x, though, that we're able to get just using distributed arrays, because our technology, it scales amongst multiple GPUs, CPUs, nodes. So there's that 35x there. So if you have a CPU, you can still get pretty good performance, right? And now, so this is impressive, right? But everyone will be like, well, of course the GPUs and everything is optimized for adding vectors and multiplying matrices. Life is much more complicated than that. You know, let's do something that's really complicated, something that could like support almost anything you imagine, right? And I completed the stream results in July. And then I was like, let me try this matrix multiply thing. I started that like 3 weeks ago. In my spare time, I am running a supercomputing center during a government shutdown, right? I mean, it's like I have got other things to do. So it's just on the side, a few minutes work here and there, and we get this. And I'm like, you got to be kidding me. Seriously, we can get this kind of performance from a high-level language? This like, all right, this can't work for everything. Let me throw something really complicated at it. Let's do associative arrays, right? These are really complicated data structures, right? They are doing all kinds of things under the covers. But it turns out it can do them as well. If you just write things the right way, i.e., you write your programs with sort of working on high-level big objects, avoiding for loops, just doing calls on whole things at a time, right? Don't call out any types, i.e., your program is just a very implicit program. MATLAB just does this for you, right? I just had to make tiny number of small changes to kind of remove some places where I was explicit about type. And I just said, no, don't worry about this, because in both MATLAB and Python, you just tag a variable as a GPU variable and then just simply uses type promotion rules for the endpoints. If I do a function on a GPU variable, it says, well, guess what? The output's also going to be GPU variable. And then the whole thing just takes care of itself. So we're getting 170x speed up on this thing that was absolutely this. If you had to pick an operation that was not in the sweet spot of GPUs, this is it. And it's doing it. And this has just absolutely shocked me, so much so that I did this like in the last 2 days. And I'm like, I gotta share this with people, right? But let's not forget the CPU with distributed arrays. There's still a factor of 25 to be gotten there. If you just have a typical high core count CPUs, that's still to be gotten if you don't have these GPUs. And that's pretty amazing. And then our metric here is token operations per second, which is, these are big numbers, 10 billion and stuff like that. But you might be like, hey, Jeremy, this is a matrix multiplication, right? And if I go back one, like the units are completely different, right? These are like 10,000 more operations, right? Well, it seems like I'm kind of being unfair to these associative arrays, because a token operation is doing a lot more than just adding numbers. It's doing all kinds of things, right? It's a much more flexible data structure. It's doing a lot of things. Well, you remember when I said there was that little asterisk next to sparse, and that how they assume the matrices were 50% sparse, and that's how you get the performance? Well, if I just do the exact same trick, right, because these things are very sparse, right, this is what I get. So associative arrays essentially dynamically, in deep neural networks terms, self-prune and self-quantize, right? Which basically means they shrink to only contain the information they need and grow as you need. Well, and now we're doing sparse token operations per second. By the same definition that we saw on the data sheet, we add a factor of 10 to the 10, right? So I'm now doing, exa token operations per second with this. Now, this is a absolute upper bound on the complexity. We would probably could come up with a different definition, but it just shows how these GPUs are forcing us to rethink computation in very fundamental ways because of their incredible capabilities. And so, either way, I'm getting 170x speed up on this with just making these very small implicit changes, making my program a little bit less type sensitive. And I will say, in every single case, the CPU version of the code ran faster too. So I have a program, there's nothing about it that says CPU or GPU. It runs faster on the CPU and gives me this performance in the GPU. Hats off to all the compiler people in these high-level languages. Hats off to MathWorks for doing this. They've been doing this for a very long time. It's very, very impressive. All right, so that brings me to the end of my talk. So thank you very much. As I said before, these high-level languages are very important. The GPUs are key enablers, and we really want to figure out how we can get this high performance with while scaling and not degrading anybody's ease of use. So with that, I will take any questions either from the audience or from the